Well, welcome everybody. It's a great pleasure to introduce Adam, who doesn't really need any introduction in this room. He spends a lot of time here lecturing, but we'll go through the motions anyway. So a great pleasure to welcome our esteemed colleague, Adam Caulton, to speak to us this afternoon. Adam read physics and philosophy as an undergraduate here in Oxford, then sadly betrayed us and went to the other place for a time that we shan't mention. So passing over that, he then spent some time in London as a postdoc and in Pittsburgh and Munich and various other wonderful places to do more philosophy of science and more philosophy of physics before we were delighted to welcome him back here in Oxford some time ago now as a tutorial fellow and associate professor at Balliol College. Adam works pretty broadly in philosophy of physics and philosophy of science more generally. And today we've got a bit of a treat of a talk which starts out, I think, in the area of important areas of general philosophy of science, and then has applications and illustrations in more specific philosophy of physicsy areas. So thanks very much for putting the talk together this afternoon, Adam, and over to you.
Thanks very much. I have to confess, the reason I chose this title, Some Mild Suggestions, Lower Expectations, because the current stage of research is still fairly inchoate. So I'm I come with sort of fairly unstructured thoughts and some concrete examples. I should also say that a lot of my thinking about these topics really got going in discussion or anything. They really got going in discussion with my students, my ex-students and my current students. So in particular, Caspar Jacobs, Dominic Ehrenfels, Eleanor March and Zach Linden. I think three of them are. Okay, so but I should say any sort of silly thing that I might end up saying will be my fault. So this is the general shape of the talk. I want to sort of just talk about intertheoretic reduction in general, sort of remind you what it is and remind you what various people have said about it. And I want to focus on what I think is an important idea that goes unmentioned because it's so obvious that it's important, the idea that reduction is some kind of deduction, but deduction in perhaps an informal sense. Then second section, I want to talk about what I call construction theory, essentially how you make the big stuff out of the small stuff, and a consideration of bridge laws. And I'm going to talk about bridge laws through two examples, in particular, John Winnie's work on Minkowski spacetime and Boltzmann's combinatorial argument, of course. It's sort of a rite of passage if you're talking about intertheoretic reduction to talk about Boltzmann's combinatorial argument. So who am I not to do that? And then finally, in the third section, I want to introduce a consideration that sort of has been brewing with various people. I just want to sort of pin it down. And I think it leads to a notion of intertheoretic reduction and consequently theoretical equivalence, which is more fine-grained than appears in recent literature. We'll get to that when we get to it. Okay, so here I think are the highlights of the literature on intertheoretic reduction. Of course, the big one is Nagel 1961. And I've sort of just put what I think the important ideas are for each paper next to the paper. I'm combining here intertheoretic reduction and theoretical equivalence. I think it's unstated on any of the slides. I'm taking theoretical equivalence to simply be bidirectional intertheoretic reduction. It seems to me that whatever theoretical equivalence is, and whatever intertheoretic reduction is, theoretical equivalence is reduction both ways. Everything I'm going to say, I think, has germs of ideas in one of these, at least one of these papers. So what I'm going to say, I don't think is going to come as a galloping shock to anyone, but I'm sort of trying to put it all in one place. So here is, if you like, the one to beat, the big account of intertheoretic reduction, what is now called the generalized Nagel-Schaffner model, or at least is in an influential paper by Fawad Dazarji Babmani from 2010. Really recommend. The rough idea is this, that to reduce a theory TT, by the way, TT, I'm following Jeremy Butterfield here with an excellent invention. Instead of talking about T1 and T2, I'm sort of getting confused about which one's which. TT is the top theory, the theory to be reduced. TB is the bottom theory, the theory that's doing the reducing. So hopefully that will make things easier to understand. The idea is roughly this, that to reduce the top theory TT, the bottom theory TB, we derive, with the aid of these bridge laws, which I'm just putting into a set delta, and some auxiliary assumptions that I'm putting into a set sigma, we derive some theory TT star, where TT star is a theory that what Schaffner calls, it's in strong analogy with TT. That notion of strong analogy is something like it has the same conceptual resources as TT, but the specific claims might not be exactly the same. So we're allowed approximations. So this is supposed to capture both exact and approximative reflection. In Nagel's original conception, these bridge laws are largely expected to be identity claims or something like universally quantified biconditionals. Nagel explicitly allows three interpretations of these. First is that they're analytic, so as it were, the terms already in use govern the fact that these bridge laws are analytic. The second is that they're, as it were, new stipulations. You make the stipulation when doing the reduction. And bizarrely, Nagel has in mind that you're making a stipulation about meanings of the terms in the bottom theory. So the thought is that the bridge laws give you extra empirical access to the concepts of the bottom theory and therefore serve as stipulations, meanings. And thirdly, empirical. The Nagel allows all three of these. And what can I say about auxiliary assumptions? Well, they're expected to be basically a confinement of PB to some particular regime, especially for when certain approximations seem valid. These are just off the top of my head. It's nice to have some examples. These are just some purported examples of reduction, right? So you may have your own favorite in mind, and there's probably hundreds that I could put on this board, but here are the ones I chose. The reduction of equilibrium thermodynamics to classical stat mech, of course, by all of the devilish details. The reduction of Galilean spacetime by Minkowski spacetime. The reduction of Newtonian gravity by GR in some low curvature, low velocity regime. And the reduction of many particle non-relativistic quantum mechanics to relativistic quantum field theory. I've got to say, this fourth one is the one I'm particularly interested in. And I'm particularly interested in the missing middleman, which is relativistic quantum mechanics, but I'm not going to talk about that. If you ask me, I think there's, as it were, a theory missing there, but never mind about that. I have to mention this one because I love it so much. Savage's 1954 representation theorem, right? So I'll just give you details of that. So what Savage says is if you've got some rich and rational preference ordering over acts, right? So acts are sort of things that you would do under certain circumstances, so long as you've got, as it were, enough of them, and you've got an ordering among them, so it's purely ordinal, which is rational. There are axioms that govern both of these ideas, some rationality. Then there is a unique credence distribution over outcomes and an almost unique utility distribution over outcomes, such that that preference ordering can be seen as maximized expected utility. So you can see the preference ranking of the acts as quantitative ranking of expected utility of these. Why do I love this representation theorem so much? Because it should be obvious that the reduction goes the opposite way, right? So if you've got a complete credence distribution and a complete utility distribution, you can derive a rich and rational preference ordering over acts, right? That's sort of boring. What's fascinating is that you can go in the other direction, or almost in the other direction. Don't quite fix a unique utility distribution, but more sort of do you want to? I put that in there because the reducing theory might, as it were, seem to have less structure than the reduced theory. In fact, these are sort of these fascinating examples, particularly fascinating examples of reduction. And I hope to talk about Savage's representation theorem again later. And then finally, some equivalence results. So Newton-Cartan theory and Galilean gravitation, that's since Alan and Knox's work and some work by Jim Weatherall and others. Vector relationism and Maxwell gravitation. This is, I think, was originally expressed roughly by David Wallace, but made completely rigorous by Eleanor March last year. I think the paper is on the archive, if anyone wants to read it. And another result by Eleanor is a kind of Newton-Cartan theory. I call it Newton-Cartan theory star, because it might not be, as it were, the same Newton-Cartan theory as up here, is equivalent to Maxwell gravitation. Which you might be thinking, well, hang on, doesn't that mean Galilean gravitation is equivalent to Maxwell gravitation? That seems wrong. So that's why you've got Newton-Cartan theory star there. Talk to Eleanor about it, because she'll convince you that, in fact, all equivalences hold for the same Newton-Cartan theory, I believe. Good. Okay, let me just make some preliminary observations about these examples. In many, if not all, of these cases, thinking of the theories in question as either a set of sentences, whether closed under deduction or not, or a collection of models, or a set theoretic predicate, or what have you, gives an impoverished impression of what you're doing. I think it gives an impoverished impression of what the reduction really achieves or purports to achieve. So I think let me just say that I think you tend to find the following features. First of all, there's some specific map, usually a functor in recent discussions of theoretical equivalence, between the models of the top theory and the bottom theory. If that is sufficient for something like deduction, the idea is that because I've got a map from the models of TT to TB, you can think of that map as we're connecting these models by some sort of intentional equivalence or something like that. And therefore, the models of the top theory are sort of held by the bottom theory. But if that is sufficient for something like deduction, it's more fine-grained, right? Because just the idea of deriving a top theory from a bottom theory doesn't imply any specific relation between the individual models. But in the kind of examples we're considering, you do have such a map or a factor. Moreover, that map tends to be constrained by some sort of explicit or implicit, usually implicit commitment that the elements of each top theory model are definable or constructible from the elements of the corresponding bottom theory. So I can go on a long rant here about categorical equivalence, but suffice to say, I think the examples of categorical equivalence that you often see in the recent literature, work by Jim Weatherall and Rita Rosenstock and so on, the relevant functor connects models such that the image under the functor of a model, the elements of that model are constructible or definable from the elements of the model. That's the object of. That was fairly clear. So in other words, it's not just you're defining any old functor, all faithful and essentially subjective, because there's not, I think, an honest commitment to these theories being categories. They're sort of hybrid things. They're categories with some sort of internal structure that we're still at. I think that's an important observation. I should also say that this map between models doesn't seem to express anything like an empirical hypothesis. I mean, sort of like, how could it? I mean, it's a map between models. It's almost a category mistake to think that. Articulate some sort of empirical hypothesis. The name of the game appears to be something like finding a relevant mirror of the top theory's models, what can be defined or constructed, or both, on bottom theory's models. And that, of course, has its most precise expression in terms of representation theory. The idea is that you've got your bottom theory and all the bottom theory stuff, you construct some stuff out of it, and then there's a representation theorem that that stuff that you constructed is isomorphic to top theory stuff. It seems to me that all of the examples that I gave on the previous slide are something like that. Okay. So going back to this idea, on all of these accounts of reduction, not just the Hegelian account, reduction is some kind of deduction. You're deducing the top theory in some sense from the bottom theory. And why should that be? So here are some things that you often see written in the literature that, well, you might have, for example, the deductive nomological model of explanation, right? So the fact that you're deducing the top theory from the bottom theory shows that you're explaining top theory using the bottom theory. Or perhaps the idea is that the bottom theory is supposed to be capturing the top theory's empirical support, and deriving the top theory would be sufficient for that. Or maybe the idea is something like the bottom theory is absorbing the top theory in the sense that the bottom theory and the top theory are not to be considered genuine rivals. They're not sort of seem to be mutually exclusive, but as it were, can be true together, right? It would be sufficient for that if the top theory is derived from the bottom theory. But look, I think those are all correct. I think it's true that reduction does all of those things. But I think that's not it, as it were. It's not really what reduction is about. Because deduction isn't actually necessary for any of those three things. Right? There are forms of explanation that aren't just deductive. The idea of capturing empirical support, well, empirical support is a funny thing, and the relevant links need not be deductive, right? In order for one bit of theory to, as it were, capture the empirical support of another empirical theory. And similarly, this idea of absorption, it's not obvious to me that deduction is really necessary for any of that. So why should it be deduction? Well, here's the idea that if the bottom theory entails the top theory, then the top theory is some inevitable, inescapable consequence of the world being aptly described or represented by the bottom theory. So if the bottom theory is true, you can run but you can't hide, the top theory is going to be true. There's, as it were, no further way the world has to be for the bottom, for TT to be a true description. As it were, TB is already true, that's all you need. And my favorite illustration of this idea is in Harvey Brown and David Wallace's objection to the de Broglie-Bohm interpretation of quantum mechanics, that if you have the resources to do de Broglie-Bohm quantum mechanics, you have a wave function. And we, Harvey Brown and David Wallace, have a program of intertheoretic reduction whereby macroscopic objects can be seen as reducing to, or theory of macroscopic objects as being reduced by purely the bit of the theory about the wave function. So you can run, but you can't hide. If you've got the wave function, you've got all the macroscopic objects you need. There's no need for the corpuscle. So supporting de Broglie-Bohm theory is sort of an Everettian, you're an Everettian in denial. Now, I'm not saying you should think of intertheoretic reduction as deduction in order to make that a good objection, right? What I'm saying is the reason that that's such a good objection to Broglie-Bohm theory is precisely because intertheoretic reduction is deductive. Of course, we could be a pluralist about intertheoretic reduction. You say, what does it have to be deduction? Can't we consider these other things? Fine. The point is that there's an interesting thing here considering. That's when it's deductive. And I should also say that no formal specification of what deduction is needed here, or indeed should be given. Because a formal specification is something like entailment in a formal language, right? So if you demand that, you're sort of lost, right? Because then you've suddenly got to cast your theory in the right formal language, right? Which no one has ever done or would ever try to do, unless some counterexamples. But you know, I wouldn't advise it. And so here I'm sort of shaking hands with David Wallace and his worries about predicate specifications. There's a second reason as well that any formal specification of what deduction is going to give you a gulf between your top theory and your bottom theory, simply because they use different concepts, right? So any attempt to connect them is going to seem like something extra, and that something extra is going to compromise the idea of reduction as deduction. The idea. Let me go into that a bit more. So if reduction requires deduction, then if we just follow the Hegelian model, it's not really that the top theory is reduced by the bottom theory. It's actually reduced by the bottom theory and the bridge laws and the auxiliary assumptions, right? And you might say, well, so what? Well, reduction by the bottom theory plus the auxiliary assumptions, rather than just the bottom theory on its own, I think seems perfectly acceptable, right? The auxiliary assumptions are just offering restrictions to those conditions under which the top theory is true. Right? And crucially, those restrictions, those auxiliary assumptions, are what you might call indigenous to the bottom theory. Right? They can be expressed purely in the terms of the bottom theory, using the concepts of the bottom theory. But reduction that requires bridge laws, I think, is more suspicious, because these bridge laws are not indigenous to the bottom theory. They can't be. Right? The whole point is to connect the concepts of the bottom theory, the concepts of the top theory. Now, suddenly it looks like what you're the thing that's doing the reducing is not just the bottom theory with these auxiliary assumptions, but this other thing, these bridge laws, which are mentioning top theory concepts, and that seems somehow vicious on the face of it. So I think there are two, broadly in the history of invertebrate reduction, two responses to this, and I think they're in fact the same. So the first is, well, actually three. I'm already assuming that two of them are the same. One from the semantic picture by Seppers, it concentrates on representation theorems, right? The whole point is that we're trying to find structures, top theory structures in bottom theory structures. And all that's required for that is just finding, as it were, the right structure that's isomorphic to the top theory structure. No, it doesn't seem that any bridge laws are required for that. Similarly, the so-called new wave theory of reduction, which sort of became popular in philosophy of mind in the 90s, has this similar idea that actually to reduce a theory, the Hegelian model isn't quite right. What you're trying to do is find some isomorphic copy, or a copy that's so-called relatively isomorphic to the top theory. But in fact, something like bridge laws are still needed, right? Because to establish an isomorphism between, as it were, bottom theory stuff or things constructed from the bottom theory and top theory stuff, you need to specify what the isomorphism is, right? And those are, if you like, the analogues of bridge laws. The second approach was David Lewis's approach. Now, the way Lewis describes it, I think, is wrong, so I'm going to describe it in my way. Apologies to him. So I think the way to see it is that really there are two species of bridge laws. First of all, there are bridge laws that are necessary for the reduction, and these are analytic. And this is the crucial point. Because they're analytic, they're not suspicious, right? So, as it were, because delta contains these TT concepts, you might think that the reduction is somehow dodgy, right? Because it's the bottom theory isn't really doing the reducing. It's the bottom theory in control of delta. But if delta only contains analytic truths, then we have deduction in the only sense we need. It doesn't have to be deduction in the sense of logical deduction. Right? It's an informal notion of deduction. So it's something like deduction where you're allowed to appeal to whatever analytic truths you like. Good, so that's one species of bridge laws. They're the ones that are necessary for reduction, but they're analytic, so it's okay. The other species of bridge laws, these are the things that Lewis actually calls bridge laws. These are the upshots of the reduction. So they're synthetic, and they're usually something like token identity claims. So Lewis calls these derived bridge laws, right? I think that's misleading because he's using a bridge law to get the top theory from the bottom theory, right? It's just that those bridge laws are not anything like identity claims, but they are doing the job of, as it were, connecting the concepts from the two theories. Now, I suggest that Lewis, Seppers, and Bickel are all trying to grasp at the same idea here. The spirit is the same, that even though we do need bridge laws to connect the bottom theory to the top theory, there's a sense in which those bridge laws are harmless. And merely a specification, if you like, of the kind of things we're trying to find that we construct out of the bottom theory stuff. And in that sense, they're close to analytic, harmless or innocent, or something like that. Okay. Good. Okay. Let's talk about some upshots of this. So if the name of the game is finding, as it were, within the bottom theory, some mirror of the top theory, or more plausibly within each bottom theory model, some mirror of a corresponding model of the top theory, it seems to me that we need two types of thing. Not the same distinction as I made before, but two types of thing that you might call bridge laws. And I think we'll run together in Nagel's notion of bridge law. The first is that first kind of bridge law that I thought Lewis was using, which is a specification of what counts as mirroring the relevant TT structures in the first place. Some specification of what the TT, the top theory stuff, looks like in order to find it among the bottom theory stuff. But we also need some account of what it is for some top theory structure to be hiding within some relevant bottom theory structure. In essence, what we need is some story about how you make the big stuff, the top theory stuff, out of the bottom theory stuff. Right? The bottom theory stuff, if you're just given the bottom theory, you're not, as it were, immediately also given the things you're looking for in the top theory. Right? If I just gave you a phase space, the concept of temperature doesn't just fall into your lap. Right? So we need some specification of how we make stuff using theory in order to find something answerable to the top theory. Good. And to preserve the ideal of reduction as something like deduction, perhaps in an informal sense, both of these things have to be something like analytic. Right? I'll tell you what I mean by something like analytic in a minute. Right? So we need some sort of specification of what we're finding. We need some sort of specification, as it were, how to produce the stuff that we can find that answers to that first description. Both of those things have to be something like analytic. And it seems to me that the something like analytic idea was explicated by Carnap. So this relates back to the previous work I've done, but let me just say, I'll just state it. But the idea is that the bridge laws and the construction theory together should be something like conservative over what, according to the frameworks of the bottom and the top theories, is trivial. In other words, if you just had the bridge laws and the construction theory together, no bottom theory, but the bottom theory sort of suggests a framework, if you like, a conceptual framework, then you can't derive anything interesting in the bottom theory from just the construction theory and the bridge laws. Simply, you can't derive anything interesting on its own in the top theory's conceptual framework.
What's the construction theory? Sorry.
So the construction theory is that second thing I wanted, that story about how I make the big stuff out of the small stuff. Now, of course, both of these things couldn't be conservative over the bottom theory itself, according to the framework of the top theory. That is the whole point. That's why you need them. Right, so it's with the bottom theory, sorry, it's with the construction theory and the bridge laws, with the bottom theory altogether, that we're finding the top theory, as it were, as a logical consequence. Right. So we don't expect conservativeness in that sense. You shouldn't expect it. The whole point is that you don't have it. But you should want to demand conservativeness, not over the bottom theory, but just over the conceptual theory suggested by the bottom theory. I'm being a bit vague about this conceptual framework business, but I promise you, be a bit more specific about it later. I'll just mention one thing. Oppenheim and Putnam did anticipate something like this idea. So they had the idea that the top theory stuff was obtained from the bottom theory stuff in mereology. Because if the bottom theory just has atoms or something, top theory has things like tables. How do I get tables from atoms? Well, I need to make some mereological fusions. Something like that idea is present here, but we need something that is vastly more general than mereology, right? Because the way that top theory stuff is made from bottom theory stuff, I think, is very unlikely to be mereological. But also, that really is only in the context of first order theories anyway, and we're not really.
Can I just ask, what does it mean to be conservative in context? Presumably not preserving, which is the usual meaning.
Having non-trivial, being non-conservative is having non-trivial consequences. You've got your bottom theory conceptual framework, and you add in bridge laws and construction theory. That, of course, allows you to construct all this stuff. And that you might think that's non-trivial, but it's not non-trivial, which is to say it's trivial by the lights of the bottom theory's conceptual framework, which didn't mention that. The point is, it doesn't say anything new or special or synthetic.
I mean, might it test the bottom theory in a new?
Sorry, what? Sorry, tell me what I'm testing.
Enable a test of the bottom theory in a new way. Would that still count as conservative?
It would allow a test of the bottom theory. Indeed, you'd expect it to, which is to say that so these things, the bridge laws and the construction theory, you would not expect to be conservative over the bottom. But it'd be conservative over the bottom theory's conceptual, what I'm calling the conceptual framework of that. So this is the framework in which you have the concepts of the bottom theory, but you're not using those concepts to say anything interesting. So there's nothing to test, as it were.
To hold you up, but I do think this is such a critical point in the talk. I mean, so take Carnap in 58. Did he explicitly advert to something like a linguistic framework with the bottom theory?
Well, he's talking specifically not about its theoretic reduction, but about if you're defining your theoretical terms. what's a constraint on your definition of of your theoretical terms? There is that, well, definition should be analytic, but what does that mean? And the idea is that it's conservative. So the thing that's, as it were, fixing the meaning as much as it does of the theoretical terms of your theory is something that doesn't have non-trivial consequences in observational terms. It doesn't say anything interesting. So I'm not using the idea in the same way that Kant used it, but it's sort of analogous. Okay, let's talk about construction theory then. So, look, I have no positive account to give you here, just ideas, just sort of intuitions, right? So I just think that there are plenty of good examples where we construct new stuff out of old stuff, and it's perfectly legitimate in the sense that I mean. So, for example, if you've got some quantities in some algebra, presumably performing those algebraic operations on those quantities to get new quantities is a perfectly legitimate way to produce new quantities. If you've got a tensor, then you can contract it to generate new tensors. But these are all ways that on paper look like a generation of new ontology that are, as it were, legitimate in the previous sense that they're conservative. If I give you a curve on a manifold, its associated tangent vector field seems to be a legitimate construction. There's a bit of an awkwardness there that it's not unique because it has to be smooth. It's only well defined actually on the image of the curve, right? Okay, but at least on the image of the curve, we should think of it as legitimately defined. Given a non-degenerate metric, the associated Levi-Civita connection that it has seems to be a legitimate construction, right? New ontology on paper, as it were, not really. Given an affine connection, its associated standard of rotation, as Weatherall defines it. Given a manifold and a point in that manifold, the tangent space of that manifold, how do you get that? Well, you consider curves going through that point. And then you consider equivalence classes of those curves. You partition those curves into equivalence classes. Right? And you find that those equivalence classes have a natural vector space structure. Gives you the tangent vector space. So that process of sort of considering arbitrary curves, forming equivalence classes, defining some sort of algebraic structure on those equivalence classes, all of that is construction, really so called, but it's, as it were, I think, innocent construction or legitimate construction. An example from quantum mechanics, if you've got some joint density operator on a tensor product Hilbert space, the reduced density operators as well, as it were, new structure, but completely legitimate. What do all these have in common? Well, what strikes me as common to all of these examples is something like the following. An interpretation of the raw materials. So if you have some physical interpretation of the mathematics, the fact that the other stuff, the constructed stuff, is made in the way that it's made from the raw materials induces a unique interpretation of the constructed stuff. Right? So something like this. If you've got a curve on a manifold, and I tell you the manifold is space-time, right? There's no choice of the matter. The associated tangent vector field represents instantaneous fall velocity. As it were, no option there. Because you already have a physical interpretation of the manifold and what a curve is, say, you should have said the world line of a material point. Right? Just no choice in the matter. That tangent vector field represents instantaneous fall velocity of that. It strikes me as symptomatic of these so-called legitimate constructions that they have this feature. That interpreting the raw elements induces a unique interpretation of the constructed elements. But that is, as it were, all I have to say, although there's vastly more to say. I'm doing terribly for time. I've got an instructive example that I can't go talk about, but let me just say that you might think this, that the more liberal our constructional theory, so the more you allow to be made for free, the greater the risk of spurious reduction. There's more stuff there, you're more likely to get a representation theorem. And some of those representation theorems will be spurious. So this is a point that, that Jeremy Butterfield and Enrique Gomes make. That may be mitigated by the second thing that I think you need, these bridge laws. Right? So if you're suitably strict about what it is you're finding, I think constructional theory can actually be quite liberal, but I'll just leave it there. I can move on. I have some other things to say about legitimate constructions, but I simply can't say them because I don't have time. I'm very sorry about that. I want to get onto bridge laws. Yeah, so I'll just go through some examples. Right, so I want to talk about Winnie's so-called causal theory of space-time. Here's what Winnie says. Wonderful paper. I really recommend you read it from 1977. He says the causal structure of Minkowski space-time contains within itself the entire geometry, topological and metrical structure of Minkowski space-time. So it's an odd missing there. An absolutely astounding claim, right? Within the causal structure of Minkowski space-time, you've got topological and metrical structure as well. Now, Winnie's inspiration is Rob, who took an axiomatic approach. So he defined an entire theory of special relativity using only one non-logical primitive, which was a two-place relation after relation. Winnie's doing something similar, but he's taking a semantic approach. So he's doing everything in terms of models. But also, he's using new ideas. So I think it's fair to say that there's a lot in Winnie that's original. Here's how to think about it. Start with the Minkowski space-time. You've got M, which is some four-dimensional affine space, rather the four-dimensional affine space, I suppose, and this thing I squared, which is the Minkowski interval to find on those points. Then strip everything out of it, apart from the base points of M, which I'll just call sigma, and gamma, which is the symmetric relation of causal connectability, right? It just means, right, 2 points are causally connected, related by gamma, if one lies in the light cone of the other, future or past light cone of the other. So he's using a symmetric relation where Rob uses an asymmetric relation, but never mind that. So just with these base points and that relation, Winnie goes on to construct, he says define, he's really constructing, first of all, some elementary concepts. Then he shows you how you can do a topology. Then he shows how you can give a linear structure. And then he goes on to give an almost metrical structure. So it's a metrical structure up to a global scale factor. You end up almost with the space-time you started with, up to scale transformations, right? So you start off with Minkowski space-time, strip everything away, apart from the causal connectivity relation, and you get back topology, linear structure, metrical structure. Amazing. So this is sort of a representation theorem that's a bit like Savage's, right? Because it looks like you're getting something for nothing. Look, when I first saw this paper, I found it unbelievable, literally unbelievable. Because I was thinking, well, isn't there this thing called Biles' theorem, which is that if two Lorentzian metrics are both conformally equivalent and projectively equivalent, then they're related by a global scale transformation. And isn't it a crucial idea there that you need both? You need both conformal equivalence and projective equivalence. So in other words, the two metrics have to agree not only on what the light cones are, but also on what the geodesics are. And it's only then that they agree up to a global scale factor. How is Winnie getting a unique metric up to a scale factor with only conformal structure? Right? It's only got light cones. Amazing. Unbelievable. And sort of related is this very celebrated EPS paper, which is sort of related to Biles' theorem, but not exactly the same thing. But a unique metrical structure can be, I say defined, I should have said constructed from a specification just of time-like geodesics and light-like geodesics. As long as they behave, they're well behaved. But crucially in that idea is that you've got some specification of what the light cones are and what a geodesic is. Right? So it's sort of reflecting this Biles' theorem idea. That's why I found this be unbelievable. So let's go into Winnie's definition to see how they are. Right. So here are some early definitions that he gives. Right. So J of some event is just the set of all of the events causally connected to that event. Seems perfectly fine. Causal betweenness. So E2 is causally between E1 and E3. If that is that E1 is here, E3 is here, then they're causally connected. Take the backward light cone of E3, take the forward light cone of E1. You've got this sort of causal diamond. E2 is causally between E1 and E2 if it's in that diamond. Okay. What's lovely about these causal diamonds is that they serve as a surrogate of open balls to do topology with. This is how he's doing topology. Good. Anyway, all to say, these seem like perfectly acceptable definitions. They're not definitions, they're constructions. These defining sets, and they still seem perfectly legitimate. Seem to follow the same sort of flavor as the examples I gave before, so the problem isn't there. So let's get into some later data. This is when linear structure starts being added, right? So you might think that's when the wheels come off, when linear structure starts being defined, because he shouldn't have notion of geodesic available. So how does he do it? Well, I'll just skip over this one. Let's go to definition 5.2. So first of all, let's define this three-place S relation. So that is defined as not the case that E1 is causally connectable to E2 or E3. And it's not the case that E2 is causally connectable to E3. And there is no fourth event, E4, which is causally connectable to all of them. Horrendous definition. Right? Once you've got that, then you define a space-like line. A straight space-like line as just all of the points that have this S relation. Right, so I've got two space-like related points. The straight line connecting them, the unique straight lines connecting them, is just the set of all points E3 connected by this two-place relation. But look, here's the idea, because this construction is intended to work for 3+1 dimensions. Thank God it works in 2+1 dimensions as well. Here's the rough idea. I've got two space-like connected events, and this one has a light cone, which I can define through causal connectability. I should have put these closer together. This one has a light cone. Where these light cones intersect is going to be a hyperbola. Right? In 3+1 dimensions, it'll be a hyperboloid. But never mind that. Now, take any point on the straight line connecting E1 and E2, say here. That point will have a light cone too. And what's crucial about that light cone is that it doesn't intersect that hyperbola anywhere. If I move slightly off the line upwards, or to the right or to the left or downwards, I'm going to intersect the hyperbola somewhere. So I can define this straight line magically just in terms of causal connectability. Isn't that amazing?
Sorry, when you said that if you have a straight line between E1 and E2, what did you mean by straight?
Well, I'm sort of giving Winnie his best shot, as it were. But let me just say it this way. I'm just going to define a straight line that way. How does he defend it? Well, it's just true in Minkowski space-time. In Minkowski space-time, this is true. That's Winnie's justification. Okay, so what is the problem? You've probably guessed what the problem is. Right. Let me just say, Winnie's account does appear to be a special case of what has become, if you like, in this talk, the working model of intertheoretic reduction. It's just that in this special case, the top and bottom theories just have one model. Right, so it's very simple. I also want to say that Winnie's definitions, they're actually constructions mostly, are unobjectionable. There's nothing wrong with the construction. Those of you who want to understand construction in terms of supervenience are at a loss here, because there's only one model. So there's, as it were, no supervenience to be had, or all supervenience is trivial. So the notion of definability has to be something stronger than supervenience, but never mind. The problem is simply this: the definitions of S, or not really the definition of S, because it's just a formal term, but the definition of space-like line are just false outside of a Minkowski space-time. Right? So if you're in a space-time that's conformally flat, that has the same light cone structure as Minkowski space-time, you will still be able to define the, as it were, straight line defined by 2 points E1 and E2. It's just that it won't be a straight line. It won't be a geodesic, or at least you cannot assume it to be a geodesic. So this is a classic example of what you might think of as a spurious reduction. You're finding, as it were, the right structure of Minkowski spacetime. So you've constructed something that has the right structure, has the structure of a Minkowski spacetime. Minkowski metrical structure, but it's not, right? If you were in this merely conformally flat spacetime, of course you would have a notion of geodesic and so on. That notion of geodesic would not align with the one you would define the Winnie way. You've, as it were, got this ghost Minkowski metric structure, is definable just from the light cones, but it isn't matching the actual metrical structure of the spacetime.
But it is unique, is it?
Yes. Yeah, absolutely. Good. So, well, I have an ugly counterexample, but if you want to ask me about it, ask me about it. I don't think I have time to go through it. I've sort of said it. What's the upshot? There's more to being a Minkowski metrical structure than merely having the mathematical structure of a Minkowski metrical structure. That's what you found. That's what Winnie's found. To be fair to him, he hasn't just found that, right? Because what he's constructed from geometrical things, right? Like light cones. So it's not, as it were, just abstract maths. It's, as it were, just the wrong interpretation. The point is, more is required to give chronogeometrical significance, to borrow Harvey's phrase, for this thing that you constructed. And I take this example to be fatal, the claim that a representation theorem alone will suffice. And I want to contrast this with Savage's representation theorem, because you might say something similar there, right? So you've got an agent with a rich and rational preference ordering, and there's a unique credence distribution over outcomes given the representation theorem. You can ask, is there a sort of a Winnie style problem there? Right? In other words, could it be that you've sort of defined this credence distribution, but it just doesn't have, it doesn't have the right interpretation, because there really is a credence distribution there and it doesn't match, right? It seems to me in that case, no. Because if you like, our only handle, what Savage is doing in the representation theorem is giving us a conceptual handle on credences in the first place. So there's nothing more to answer to. Does that make sense? He's really advocating, if you like, a conceptual reduction of what it means to have, say, credence a half in the coin counting up heads in terms of rich and rational preference. We can't do that here because we already have a conceptual what Minkowski spacetime structure is. I think that's helpful. I wanted to talk about Boltzmann's combinatorial argument, but I don't have time.
15 minutes, we started a bit late.
Oh, maybe I do. Okay, good. Okay, here we go. This isn't exactly what Boltzmann did. It's inspired by his argument. So we're considering a monatomic gas confined to a cylinder, and here are our goals. Here are Boltzmann's goals. I'm just telling you what they are. First of all, we're going to derive the Maxwell-Boltzmann distribution as the unique equilibrium distribution of this gas. We're going to derive the energy identity equals 3/2 nkt, and we're going to derive the ideal gas law. And just for free, we're going to derive the Sacco-Tetrode equation too. Right, so we're going to derive a significant amount about the thermodynamics of ideal gases of this. You may know how this goes, right? We consider this thing called mu space, which is the phase space for a generic single molecule. Force grain the mu space into finitely many cells of equal volume, phase space volume. And each cell can be associated with a mean energy, right? So the important assumption here is that the total energy of the gas is roughly just the sum of the energies of the individual molecules, right? So the idea is that collisions are happening so rarely, most of the time the total energy is just distributable among the individual molecules. Because that's true, you can associate these individual cells in the single particle phase space with an associated energy. Each microstate in the original phase space for the full gas determines a unique distribution of occupation numbers, telling you, as it were, how many particles are in each cell in mu space. And that distribution determines a region of the phase space with a particular volume, and it's that volume. And the equilibrium distribution is the one for which that's maximal, essentially, right? So you've got the Boltzmann definition of entropy, trying to maximize the Boltzmann entropy. Subject to the constraints that the total particle number is that and the total energy is that. Now that has a unique solution, right? You have to use Stirling's approximation and so on, and other approximating assumptions, but essentially what you get out is that there's a unique solution, which is this. You've got two constants. Z is essentially just a normalization constant, although it doesn't have interesting information in it, and this other constant beta. Now beta is associated to the total particle number and energy like this, right? It has to be in the derivation, right? And we already know, by the way, that if a reduction is possible here, saying that it is, but if it's possible, then this constant beta must be a function of the temperature, right? because beta is parameterizing equilibrium macrostates. And temperature in thermodynamics just is the thing that parameterizes equilibrium macrostates. So we know we should expect some functional relationship between beta and the temperature. Okay, but we know more than this. So if we just take the first law of thermodynamics, the partial derivative of the entropy with respect to the internal energy with the volume is just it's just the inverse temperature. But we've derived the Maxwell-Boltzmann distribution with the Boltzmann entropy, and we've got a notion of energy that's indigenous, as it were, to our classical Hamiltonian theory. That gives us the result that sort of analogous partial derivative is k beta. So that, and so now all you need is to identify the thermodynamic entropy with the Boltzmann entropy, at least approximately, and the thermodynamic internal energy with the total energy in the Hamiltonian theory, to get out that beta is what you thought it was, which is 1 over kT. It immediately follows from that that energy is 3/2 nkt. And if you have a bit of other funny business, considering what pressure is, you can equally derive PV equals nkt. And let me just say, there's a sort of Gibbs twist as well. You can derive the Sackur-Tetrode equation by moving from what I call specific to generic phases. An extra bit anyway. Let me just give some observations about this reduction. We're not just deriving equations here, although I've presented it that way. We're deriving the structures which give sense to those equations, right? So in other words, you've got a unique equilibrium macrostate at any value of the internal energy U and the volume V. So as it were, I'm not just deriving EV equals nkt. I'm deriving all of PV space, right? And the foliation of PV space by isotherms. Should I say? Each equilibrium macrostate also has a unique. Oh, said that. So it has a unique pressure. You get PV space. The identification of the temperature T went in some sense via the laws of thermodynamics, right? So in particular, I used that identity. For that identity, you need actually the 0th and the 1st and the 2nd laws. You also need the -1st law to justify this identity. But I've not said anything about that. So I'm only giving you a partial picture here, right? In a sense, what I'm doing is showing you how you get temperature out. And it looks like I've cheated because you have to sort of assume these bridge laws, right? Believe me, you can derive these as well. Just haven't given you the full story. But the full story for deriving this involves using the -1st law as well. Good. Now I said in some sense they go via the laws, but in what sense? In this sense, the laws themselves don't need to be assumed, this identification. This is sort of a tricky thing. All you need to assume, as it were, is that if there are quantities that answer to the description as given by thermodynamics, then these are they. But that is a much weaker claim than the laws themselves. In fact, it's an analytic claim. That's all you need. It's actually through an analytic claim or a series of analytic claims and other details that I'm not giving here that you get finally to beta equals 1 over kT. So I think this is a case of successful reduction, even by these stricter standards. That's the point. So Winnie was supposed to be a bad case. This is supposed to be a good case. Okay, let me just say a few final things. I've said this before, but let me say it again. In many, if not all cases of interest, a physical theory isn't really a set of sentences or a collection. It's not just those things. A physical theory tends to give you a state space or something like a collection of kinematically possible models, right? You're doing quantum mechanics or classical mechanics, it's usually a state space, right? If you're doing space-time theories, it's APMs. You've also got an associated collection of quantities. Those quantities have some algebraic structure and they're defined over all of the KPMs or over all of the state space. And we have the dynamical laws, right? Thinking of a theory just as a set of sentences, of course, those sentences are these, right? It's the dynamical laws bit. Or as a collection of models, you're normally just thinking of the DPN, right? what I called before the conceptual framework of a theory is really this full space of KPMs and the quantities defined on them. The idea. The point is that physical theory provides a framework in which very, very many claims may be expressed, not just the dynamical laws. Yes, the laws as well, but also initial and boundary conditions or any number of other contingent claims. Right? As it were, got a mini plurality of possible worlds there with which to construct a variety of propositions. Right. So what I'm going to propose is that we start caring more about these KPMs. And you might say, well, why should I care? I'll tell you why. But we should care, and in fact, I think we do care more about more propositions than just the conjunction of the dynamical laws. If the reduction of a top theory by a bottom theory plus some auxiliary assumptions is truly by that bottom theory plus the auxiliary assumptions alone, then the resources we need to carry out the reduction through the bridge laws and the construction theory that I've been talking about, those in fact provide the resources to find that any proposition you like in the top theory's framework, some corresponding proposition in the bottom theory's framework. In a translation scheme, it's not just here are the dynamical laws up here, here's how you express it in the bottom theory. Take any proposition of the top theory you like, here's how you express it in the bottom. It's also generally false, right? So you might say, I don't care about the mere KPMs because it's only the DPMs that receive a physical interpretation. But I think that's false, generally. And the main reason it's false is that, people often talk about representation relations, right, between models and possibilities as a way of thinking about interpreting a physical theory. But these KPMs or DPMs, which are mathematical, and you're trying to sort of give them this sort of physical juice, right? So you imagine this representation relation that takes you to a genuine physical possibility. That's not a bad way of thinking about it, but it is a bad way of thinking about it if you're thinking that it is that coarse-grained. Right? The point is that that representation relation between models and possibilities, more often than not, is induced by a representation relation between the elements of the model and bits of the world. And if that's true, then I'm sorry, you don't just get an interpretation of the DPMs. You can't help it. You also get an interpretation of the KPMs for free, right? And it's a good thing too, right? Because we don't just want an account of what the world would be like if the theory were true, to sort of paraphrase Van Fraassen, but also what the world would be like if the theory were false. After all, the dynamical laws are sort of things that we want to subject to tests, right? So we want to know what would the world be like if these dynamical operations were false. But aside from all this, there's a knockdown argument I want to give, borrowing from Eleanor March's result. Here's a reason why I should care about mere KPMs. If you want to know what geodesics material bodies follow in the vacuum sector of Newton-Cartan theory, you cannot use the geodesic principle because you don't have a unique connection. Here's what you can do. You can consider models which are like the model you care about, except you've got a bit of matter where you wanted to put the matter, right? What are such models like? Well, they're almost exactly the analogues of David Lewis's small miracle worlds. So these are worlds in which the DPMs are not satisfied because you've, as it were, magically put a bit of matter there. But you're considering precisely those models to, as it were, see where the matter goes. This is just to say that Lewisian idea of looking at these small miracle worlds to assess counterfactuals has an exact realization in vacuum Newton-Cartan theory. I hope I'm not saying anything wrong.
That's exactly right.
Okay, good. Any more questions, direct them to Eleanor, not me. Good. Here's a bit more, what I'm about to say is a bit more controversial and a bit more fruity, but I'll say it anyway. The KPMs of a theory are tied closely to that theory's ontology in the way that the DPMs aren't. Specifically, what is necessarily true given the ontology appears to be the same as what's true in all KPMs. So if reductions are going to be legitimate or genuine, if reductions are legitimate or genuine insofar as they reduce not only the laws but also the ontology, then legitimate reductions must look at the theory's KPMs. I'm thinking of looking at KPMs as sort of a surrogate for looking at the ontology. We don't have to go into predicate precipitations or any of that business. Just look at the KPMs. Another thing that I want to say is that distinctions between theories that are invisible from a pure focus on DPMs become visible once KPMs are considered. And I just don't have time to justify this. So if you want to ask me about it in the Q&A. But I just want to say that you may believe that your partner has the same theory as you because you agree on what the DPMs are. And you're only looking at the DPMs. But if you looked at the KPMs as well, you'd realize that, well, the sort of KPMs that they entertain, you don't entertain. I want to suggest that really that's a sign that you're got different theories in mind. So distinctions between theories become invisible when you only look at the DPMs. They're invisible when you look at the KPMs. Am I all right to just?
Yeah, there's.
Good. So here's the current proposal then, just to sum up. A bottom theory TB reduces a top theory given some auxiliary assumptions. So I'm just making the auxiliary assumption explicit in the relation there. So it's a replace relation. If and only if there is some TT star, this is following Schaffner, in strong analogy with the top theory, such that, right, deep breath, there is a map from the bottom theory's KPMs, which obey the auxiliary conditions, to the top theory's KPMs, which is surjective, or essentially surjective. So in other words, you're recovering all of the top theory's KPMs. And that map is kosher by the lights of the constructional theory. In other words, for each bottom theory KPM, the top theory KPM related to it contains only structure constructible from that original model. Or to be more precise, contains only structure which is isomorphic. And it has to be kosher by the light of the bridge laws, which constrain which constructions from your bottom theory may be identified with which top theory elements, right? So just to review, what goes wrong with Winnie is not this, he's got that, not that, because he's got that, not that, because he's got that, that one. And finally, the map should only map the bottom theory's DPMs to the top theory's DPMs and the non-DPM KPMs of the bottom theory to the non-DPM KPMs of the top theory. So it sort of respects the DPM via KPM split. Right, what are the upshots? First of all, many of the purported reductions that I earlier listed, if you can remember that far back, are still successful according to this stricter model. I think that's an important observation. It also means that the implied standard of theoretical equivalence, remember for me, theoretical equivalence is just two-way reduction, is now more fine-grained than what I call categorical equivalence plus. So in discussions, particularly by Jim Weatherall and others, right, they use categorical equivalence as the standard. I think they're secretly using stricter standard that I call categorical equivalence plus. My standard is more fine-grained than theirs. However, I do suspect, though I haven't proved it yet, that my implied standard of theoretical equivalence is going to be equivalent to categorical equivalence plus of the DPMs, what they want, and the KPMs, which they don't consider. So it's a more fine-grained notion of theoretical equivalence just because of that extra condition. It's still a categorical equivalence condition or a categorical equivalence plus condition, but it's applied at the level of the KPMs as well. What happens if you've got a more fine-grained standard of theoretical equivalence? Well, some theoretical equivalence claims now fail. What are some nice examples? Weatherall's electromagnetism with the Faraday tensor and electromagnetism with the electromagnetic one form are no longer equivalent because the closedness of that one form is, as it were, a mere contingent fact. The Faraday tensor, sorry, you can't escape it in the second theory. So the KPMs don't match. And well, I'll just point to a lovely quote from Simon, which I haven't put on the board, about why Newton-Cartan theory can't be equivalent to Maxwell gravitation. It essentially comes down to the fact that there are KPMs of NCT, of Newton-Cartan theory, which, as it were, have no mirror in Maxwell gravitation because, as it were, not enough structure to define them. Good. I'll just say, see Eleanor March, who will restrict the structure of NCT suitably so as to restore that equivalence. But even that is significant. It still goes against the traditional equivalence claim. Right, I'll stop there. Thank you very much.